Okay, good evening everyone. My name is Julian Schwarzenbach. I'm chair of the BCS Data Management Specialist Group, and welcome to tonight's webinar on explainable artificial intelligence. Just a quick explanation of what we're doing, how we're running it. So I've got Ed Evans and Glenn Val from the Data Management Specialist Group Committee helping me run the webinar here. Julian Hatwell, our presenter, he's up in Birmingham. And so he's going to do a presentation for about 20 minutes or so and then answer Q&A at the end of it. So if you've got a question to ask, if you can type it into the chat console at the bottom of the GoToWebinar box at the side of the screen, we'll then sort of take those towards the end of the presentation. Quick reminder about some upcoming events that we've got. Next week, a week today exactly, we've got an event on titled Spatial is Not Special, Adventures in Location-Based Data. So that's if anybody's got interested in geospatial data and mapping and spatial analysis. We've got a gentleman called Thierry Gregorius, who's got a lot of experience in oil and gas and quite a few other sectors, coming as our speaker. And then we've got a session on the 28th of October, which is looking at the deadliest sins of knowledge management and how to avoid them. And that's a joint event with CILIP, the Chartered Institute of Library and Information Professionals. The presenter is Judy Payne, who was one of the authors of the ISO standard on knowledge management that came out a year or so ago. So that's the housekeeping and the publicity for the forthcoming events out of the way. So what I'll do now is hand over to Julian. So he's a PhD student, so he's 2 years into his PhD. And sounds like it's quite interesting what he's got lined up for us. So over to you, Julian.
Thank you very much. Thanks for this opportunity to present for the British Computer Society Data Management Specialist Group. Let me introduce myself a bit before I dive into the content. I'm actually a mature student. I've got about 15 years experience in management information and BI, mostly in the for-profit education sector. I worked out of London and Singapore. A few years ago, I took a career break to do a master's degree in business intelligence at Birmingham City University. That was a very thoroughly modern take on BI, and there was a significant component of data mining and machine learning content on that degree. One thing led to another, now doing research towards a PhD, designing explanation systems for decision forests, and that's something we'll touch on a bit later in the presentation. So the first thing I'm going to do is just quickly introduce machine learning and specifically the black box problem. When we do machine learning, we take historical data or training data and feed it into a machine learning algorithm, and then the output from that algorithm is a model or a kind of summary of the training data that allows us to do predictions or automated decisions on new data. That's data that wasn't contained in the original training set. And the state-of-the-art methods that we have give us very high predictive accuracy, but they're hardly interpretable. Explaining how they make each individual decision is very difficult, and that's because of the way that maybe data is represented inside the model, or a very complex internal structure. So, for example, the image on the left that we can all see, we can interpret very quickly as a handwritten digit number 8. But for a neural network to classify this digit, we have to provide a numerical value for each individual pixel, and then these values are transformed mathematically or computationally across many different layers until the output that this is a number 8 comes out of the other end. So it's obviously very difficult, or in fact impossible, for us with our human cognition to unpack what's going on inside this model. Another example is decision forests. These are the kinds of models that I work with. I'm sure lots of people listening in will be familiar with decision trees. Decision trees are very interpretable models. They're just a hierarchical structure of binary rules, something that must be true or false about your data. But a random forest, for example, on the left-hand side is tens, hundreds, or maybe thousands of decision trees generated from random start conditions and then operating in parallel to give a majority vote. On the right-hand side, we're looking at a boosted model, and this is generated sequentially with each new tree added to the model, trying to correct the errors of the previous iteration. Now, you can probably deduce from that looking at a single tree from one of these models isn't going to give you any information about how the whole model is going to behave. And obviously, it's very difficult, or again, impossible for us as humans to contemplate all of the trees at once. And in fact, it's a difficult computational task to do as well. When we talk about machine learning classification, I think it's useful to quickly look at what's going on in 2 dimensions. Here we're trying to find a separating boundary between these clusters of data that you can see superimposed on the 2 graphs. They're not very nicely behaved clusters, they're very interleaved. And on the left-hand side, I've got a logistic model, and that essentially tries to find a straight line to separate these data. This is very interpretable because it just comes with a very simple mathematical equation, but it's not very good at separating these particular data. On the right-hand side, we're looking at the boundary generated by a random forest model, and this perfectly separates all of the data, but we don't have any way to describe this line mathematically or in simple language. In fact, the only way to generate it is to produce a classification for every point on the grid and then draw the line in between points of opposing classes. So I have a very simple model that that isn't very accurate, or a very complex model that is perfectly accurate. So there's always this accuracy-interpretability trade-off when we're choosing which model to use in machine learning. Now, let's move on to the legal, moral, and ethical issues that are thrown up by this black box problem. I'm sure lots of people listening in, anyone who regularly watches the TV or listens to the radio will have noticed an increasing number of news items or current affairs features discussing AI and the effect that that's going to have on society, the impact that that's going to have. And then, you know, we hear all of these concepts around big data, profiling, micro-targeting of advertising content, and more controversially, political messaging. And people are aware, I think, that their social media feeds are curated by algorithms, and perhaps less commonly thought about, even search engine results. So the results that you and I might see for the same search terms might be quite different depending on our digital profile, on the things that we've been interested in or interacted with in the past. So this idea that all the things that we see and do in the digital space are actually controlled by algorithms that even the people who own these models don't fully understand, that justifiably raises a real lack of trust in the public discourse. Another problem, as with all things related to data, it's a question of garbage in and garbage out, and this is best manifested in machine learning research as when we have bias in our training data. Now, this causes some really serious problems. Just today, I've seen a report about a system that's meant to identify faces from passport photos. And it doesn't do very well on Black and ethnic minority faces. And that's purely because of the proportions of Black and ethnic minority faces to Caucasian faces in the training data, in the photographs that have been collected in the past and used to train that model. A much more serious problem, well documented in the United States. A number of states tried to implement a machine learning system for generating a risk of reoffending score for prisoners coming up to parole. And this model, it turned out on a statistical analysis after the fact, was giving very unfair decisions towards African Americans. So machine learning can only learn the bias that exists in the data. it can't fix it unless we actively take steps to do so. And we can only do that if we have transparency, if we can bring to the surface the issues caused by bias in our training data. Now, again, I think lots of people listening in will have had experience getting their systems ready and compliant for the GDPR, but I dare say most people will have spent their efforts on the governance side of things, so security, privacy, provenance, and access, and the ability to delete and the right to be forgotten and so on. But the GDPR also contains articles relating to automated decision-making and profiling. And without going into lots of detail about that, what it boils down to is people have a right to an explanation about any decision made about them that has a significant effect. And so that means a human, a real person, needs to be the final arbiter of any decision, any such decision that's made. Now, why this right to an explanation isn't something new. It's been around since since 1970, the Fair Credit Reporting Act. But that was obviously during a time before people were envisioning all of this automation of high-skilled, knowledge-based professions. What we're also seeing, obviously, is the very broad reach of the GDPR and automation of all of these high-stakes decision-making areas. So while I think people working in financial services probably have this area of GDPR fairly well covered, one of the biggest areas of risk that I think maybe haven't been fully considered is what happens when we automate all of these public sector services, the kinds of things that are listed here on the slide. So there aren't any test cases right now. There's not any legal precedents because the GDPR is fairly young legislation. It's only been fully enforced since May of last year. But the regulator has demonstrated an appetite to apply penalties in other aspects of the regulation. So I think it's only a matter of time before we see the first litigation under the automated decision-making articles. And where does this leave us? So looking back at the black box problem that we described earlier, this poses a significant barrier to adoption for state-of-the-art machine learning methods for organizations that are implementing or intending to implement automated decision-making. And we see that in financial services, a number of companies sticking with things like logistic regression because they understand that, and that comes with decades of statistical theory behind it. So let's talk about the good news, which is that initially a niche community in machine learning research, but now a much more active area, have preempted and responded to this issue. We've seen the search term explainable artificial intelligence appearing around about 2016, and that has become the de facto term to describe this research area. Before that, it was less well-defined terms like black box and interpretability. And this is from a search that I did of the Google Scholar, which is an academic search engine. And I was looking at the number of hits for machine learning and the proportion of those that contained one of these other search terms. And we see from quite a low base in the late noughties, suddenly very rapid growth in this research area. And I think the watershed came around about 2017 when the Defense Advanced Research Projects Agency announced a very well publicized call for funding applications. So that's the largest strategic government agency in the US announcing to the world that they have a lot of money to spend on projects and teams working in this research area. So let's think about how we would do explainable AI or interpretable machine learning. And the first thing to do is think that a model isn't going to exist in a vacuum or just on some researcher's computer in a lab. In order to be useful, it's got to be deployed into a system of integrated processes. And downstream from this model and its decisions is going to be a human, a real person, as the end user or consumer of those decisions. And they have a job to do or a task they need to complete, and they are hindered from doing so because they don't have access to the chain of reasoning that led to the decision they have in front of them. In the days before automation, there would have been someone they could ask, but that avenue is now closed to them. So one thing we can do is just try to make more interpretable models, and that's a perfectly valid area of research. There's a few listed here, which people can follow up in the references after this webinar. Most of these models take the form of a cascading rule list, and that's really because logical rules are the de facto language of logic and reasoning. Essentially, these models just differ in the way that they're trained and the way the rules are derived. What I would say is they still suffer ultimately from the accuracy-interpretability trade-off. What these models still do is simplify and summarize something that would have been more completely captured by a more complex black box model. So there are limitations here. The more active and current area of research which I'm working in is in providing explanations in real time as each decision is made by the model. And an explanation then is a unit of additional information that gives the consumer the knowledge that they need to reason and interpret about the decision that's been made for themselves, and then they can fully complete the task that they have downstream. I think these various methods divide quite neatly into two different axes. So on the left, I've got model agnostic methods, and they're supposed to work with any kind of black box model. And on the right, there are some model specific methods which are tightly coupled to specific types or families of models. So some of them work only with decision forests, some of them work with neural networks, and so on. On the top axis, we're looking at additive feature attribution methods, and at the bottom, classification rule-based methods. And this axis talks more about the form of the explanation, what that explanation actually looks like to the end user. So we'll have a quick look at additive feature attribution methods. What we're seeing here is we've classified an individual as belonging into the lower income bracket, less than 50K US dollars per year. And the feature attribution method finds the most important attributes that led to this decision being made and assigns a numeric value that tells you the relative importance of that attribute. And in this case, we've got 4 attributes that all are pushing towards one particular decision, and 1 attribute that's competing and trying to head the decision in the opposite direction. But in totality, in their summary, the decision was that this individual has less than 50K. At the top, we're looking at something called Shapley values, and at the bottom, we're looking at the output from a system called LIME. Again, the references are in the slides, and that's something that people can follow up later on. A classification rule-based method comes up with a classification rule. So that's an X that implies Y. So an explanation implies the decision that was made. In fact, to generate such a rule, what we do is work backwards from the outcome from the decision. So we start with income is less than 50K, and then looking at the attributes of that particular instance, try to match that up with the historical data that we have and determine the rule that covers as much of the historical data with the best possible accuracy. So in this case, we found a rule that covers nearly 40% of the historical data and matches 97% of those 40% that were covered. So this is a very good quality rule. It's a very helpful rule. It's actually a piece of information that we can save and store away to use later. It's very clear when this rule applies to another instance, which is not the case with feature attribution methods. So there's the advantage of using classification rules. In terms of whether you would choose a model agnostic method or a model specific method, well, model agnostic methods sound pretty smart. They sound pretty clever because they can work with any method. And the way they do that is that they just require access to the inputs and the outputs. And they take the instance that you want to classify and explain and generate a synthetic sample that are all very similar but slightly different to that instance using randomization. And you pass that synthetic sample into the model and then look at the outputs and do a statistical analysis that lets you determine which were the most sensitive inputs that that when they're changed lead to a change in the output. So this works really well for image and text data in particular, because generating this synthetic distribution just means switching pixels on and off, or adding or removing words from a snippet of text. But the assumption is violated for tabular data, and the reason for that is that you have to refer to the training data in order to get the valid inputs for each of the variables. So essentially, what is the domain and distribution of each of the columns in your data table that you're trying to analyze? Once you've accepted that you're touching the training data, you kind of fall out of the remit of a model agnostic model. The other thing I would argue is the scenarios where you really need a model agnostic model are quite rare. I can only really think of third-party audits where you're trying to assess the quality of somebody else's model. And in that case, you mightn't even have access to the inputs, or they might be rate limited behind an API. So it might not be possible for you to send in as many samples as you need in order to do a decent statistical analysis. So the short answer to this question really is, if you're the owner of the data and the owner of the model, and there's a model-specific method that matches your model, it's almost certain that that method is going to be more stable, faster, and give you better quality results. So you use a model-agnostic method where you don't fulfill all of those criteria. I think the last point I would make on this is how to quantify the benefits of applying XAI in maybe an AI transformation project. So it's very difficult to measure the quality of an explanation or the interpretability of a model. That's something that's quite qualitative and not very easy to define in any formal way. But the suggested approach, which is really common sense, is to focus on the improvement in task performance. That's something that you can measure more easily, and while it's not a direct measurement of the quality of the explanations, it's very likely to be a direct measurement of the thing that you wanted to improve in the first place. So this clearly is, the common sense approach and would be the recommended way of doing things. So I'm going to wrap up there and just repeat the points that I made, essentially, that there's a big trust deficit generally around AI and its impact on society, and the black box problem certainly doesn't help. More concretely, the GDPR poses clear risks to organizations using machine learning for all kinds of high stakes decision making. In business, I think that would affect how you offer products and services, but also things like HR processes. We didn't touch on this so far, but GDPR quite specifically covers things like assessing employee performance and productivity. The good news is there are novel solutions. There's a lot of research going on in this area, and we're actually seeing this stuff filter through into commercial applications. So it's available in common machine learning libraries for Python and R, and I'm also seeing it in commercial tools like RapidMiner, which I use in my teaching. So with that, I think I can hand over to our hosts and see if there are any questions that have come in.
Right, thank you, Julian. That was a very nice, clear explanation there. Yes, so if you do have a question, if you type it into the bottom of the chat console, then we can see that here, and we'll then ask those across to Julian. So just an opening one really is in terms of just your thoughts really in terms of where artificial intelligence and machine learning is most successfully applied in the commercial world. Have you got any thoughts on that?
I think it's certainly been applied very successfully in terms of recommendation engines. That's, I would say, clearly where it's delivered the most commercial value. You look at a company like Amazon, and their whole business model is pretty much based now on recommending to you things based on what other customers have bought who may be similar to you in terms of their buying profile and their viewing profile and the things they're interested in. So that's my kind of quick and easy answer to that question.
Okay, yeah, good. And so in terms of the, if you look at the training data sets, you talked about bias earlier. So how do you actually sort of reduce bias in the actual training data? So there might be bias in the algorithms that you're developing, but also you may also have bias in the training data.
Yeah, I mean, essentially that's the point I was making, that lots of the training data that people use contains inherent bias because society has been inherently biased historically. So the example I gave about the system for identifying faces from passport photos, it doesn't do very well because there haven't been enough Black and ethnic minority faces in the training data. So, you know, you could only correct for that bias by finding the right balance, essentially, showing the system more Black and ethnic minority faces. What XAI, explainable AI and machine learning, ought to be able to do, if it's successful in its implementation, is allow you to bring to the surface all the areas where your model is flawed. So just essentially discovering that problem, that it's not doing very well on Black and ethnic minority faces, is something that explainable AI would definitely bring to the surface.
Yeah, okay, so interesting follow-on questions come through from Mark Ainsworth. He was asking really in terms of actually how would you identify if you've got bias in your training data?
Well, essentially, using these procedures, you would once you've done your training, if you're doing machine learning the right way, you've held out some data to test your model on and test its efficacy and its quality. If you've implemented explainable AI and machine learning, then you'll be able to do an analysis of the explanations that you get. So, for example, taking the classification rule-based explanations, you can do an analysis of how frequently certain search terms appear, and then how accurate those classifications were on that particular subset of the data. So if you think we're struggling to classify certain types of instances or certain types of inputs, you can see how many search terms or how many attributes have been used, and that's shown to you by the explanations themselves.
Yeah, okay, that's good, thank you. Yeah, just a quick reminder, any more questions, if you just want to type them into the console, we can see them here, we'll ask them through across to Julian. So another one really is in terms of just thinking through about when you're programming your AI engine, how much extra time and effort is needed to sort of add in the explainable aspects over, if you like, you're doing it conventionally, where you won't have to worry about explaining it? Well,
hopefully, let's say you're using it. It's kind of the same as it would be for setting up a machine learning process. So let's say I'm working in R or in Python. I would take an existing library that will build a model for me, and then hopefully, because enough research and work has done, there will be libraries that are there to explain models as well. So for instance, I'm developing a Python library. So in an ideal world, it won't be a lot of additional effort because you'd be able to just tap into the work that I've already done, or the people who have built Shapley values or Lime. You just add that on to the pipeline that you have. So I would say it shouldn't be lots of extra work, because any common sense approach would be to reuse stuff that's already out there, unless you want to you have a very, very specific use case that requires you to develop something from scratch. But in that case, you're in the world that I'm in, which is doing a PhD to get that far.
Yeah, okay. But I can also think of scenarios where you may come up with a specific rule set, but actually documenting it and describing that as you develop it is probably similar to just commenting code. If you're doing more conventional programming, as long as you're doing it the right way, it should be there for the future.
Yeah, and one of the nice things as well about, say, the classification rule-based approach that I'm working on, and that some other people are working on, is that you can collect the classification rules as you explain new instances, and over time that becomes an interpretation of the whole model itself. Assuming that collection doesn't grow too big and too complicated, or you find ways to prune it down, you maybe then have a way to actually describe a lot better the overall, the holistic behavior of the models that you've developed. So I think there are lots of benefits to doing it that way.
Yeah, good. And sort of a related question from Alan, who's really asking if there will be, if the explanations will be sufficiently clear to explain how, for example, somebody's insurance premium has been calculated.
Well, this is very task dependent or domain dependent. Now, I would hope so, because you saw from the outputs of Lime and of Chirps, my algorithm, that the outputs relate directly to attributes of the input data. So in that particular case, it was classifying somebody as having a high or a low income bracket, and that might be, we might substitute that classification with whether we give them a loan or not. And so hopefully you could see from those examples that actually it should be very clear, because we're directly referencing what's going on with the input data. There is another aspect to this, which I haven't touched on, which is that good explanations should give you an idea of what would happen if you change the output. If you don't mind, I'll backtrack onto the slide that shows this again, and you can see the contrast column here tells you what would happen if I took one of these rule terms out of the rule. So here, this L capital gain factor, if I took this out of the rule and only had these other two rule terms in there, I would lose 80% of this 97% of precision. And that essentially is telling me I would be getting the opposite. I'd be getting the opposite classification, that would be classifying this person as having a very high income bracket, or potentially would be happy to offer them a loan or a financial product. So it's very important for explanations to be able to provide this contrastive, or what's described in the literature as counterfactual information that tells you what would happen if something was different, or what do you need to change to get a different output. That's a very, very important feature of a good explanation.
Yeah, okay, that's good. Had a question come in, and it's one that I should have covered earlier on actually, is that we are actually recording this webinar, and once we process it, it will be going up online on YouTube on the BCS member groups channel. There's a specific playlist in there for the data management specialist group, and so we'll add it to that playlist. And so there's a question there about the recording, so yes, we will definitely be doing that. Another question then is, in terms of what significant developments do you expect to see in the next couple of years?
That is a good question. I'd have to stop and think about that because I'm so focused on what I'm doing. I'd love to imagine that that the work I'm doing will be a significant development in a couple of years. But I think the most important algorithms that have come out that have really been talked about, not only in the research community but much more broadly, are two algorithms. One called Lime, which I presented to you on the slides, and another one called SHAP, which is SHAP, and that uses Shapley values as its underlying theory, but it's got really good visual interpretations of what's going on. It can do really nice summaries of your model's behavior and a very good visual, intuitive interpretations of the explanations. So that right now, I would say, is gaining a lot of interest, a lot of popularity, and I dare say it might even become the norm. It might become bread and butter in just a couple of years. It's the visualization piece that I've seen integrated into RapidMiner, which is a commercial data mining software. And I think it's probably going to catch very significantly.
Okay, yeah, that's good. And Mark's asked another question, which is maybe a little bit more techie here. It's that if the explainable artificial intelligence explanation is based on the use of rules inferred through machine learning, does that actually undermine the understandability of the AI decisions? That makes sense.
Does it undermine it? Does it undermine the understandability? Is that the question?
Correct. Yeah.
I don't see how. I mean, unless I'm missing something, I can only see it as enhancing the understandability. The rule is generated after the fact, so it's a post hoc explanation. We do we build a standard machine learning model like a random forest, get it to classify a data instance, and then take that classification and query the model to find out a bit more about how that classification took place, and then present additional information. So I can't see it undermining the understandability of machine learning. I can only see it enhancing and augmenting it.
Yeah, okay, that's good. I think we're sort of running through the questions we've got there. So if there's anybody else who's got any questions, just add them in onto the chat window. We'll answer those as we get to them. I mean, one of the experiences I had a few years ago, I had the pain of trying to get an artificial intelligence system finished off for use in utilities, and doing some modelling there about asset replacements. And one of the challenges we had there was that you would run the model, it would come up with an answer, you'd tweak an input parameter very slightly, you'd run the model again, and the output would actually be a completely different answer, and you couldn't work out how you got from one to the other. Now, maybe explainable AI in that situation might have helped us understand both how we got the first answer and why the second answer was so different.
Yes, I mean, I firmly believe that if you'd have had XAI capabilities on that project, that would have really helped you. The nice thing about XAI is it will help you understand the interactions between features. So what you were saying was that when you changed one feature very slightly, something completely different came out the other end. And unless you have visibility on how different features are interacting with each other, it's very hard to predict what changes are going to give you changes to your output. You know, you might make a really large change to the very same feature and end up with an identical output to the one you started with, because you just can't see the interactions and the non-linearity between that's between the input feature and the output. XAI is definitely something that could address that blind spot.
Yeah, okay, that sounds good. Yeah, good. Okay, so I think that's all the questions we've had online so far, plus my additions added in there. Thank you very much for your time, Julian. It's been a very clear and thought-provoking presentation. As mentioned earlier, we will be posting the recording up on the member group's YouTube channel, and that probably be within the next week. So if you look on there in a sort of few days up to a week's time, then we should have the recording there. So thank you for all those who attended. Hope you found it useful and informative. Quick plug again, next events and the listing is available on the Data Management Specialist Group website. Next event is this time next week, which is our session on GIS data. And then on the 28th of October, we've got a session on knowledge management and how you manage that. So just like to sort of thank you for your time and hope you all found that useful. So thank you very much.